Hello, everyone, and welcome to today's graph reading group.
And we've seen the impact that diffusion models have had in the research field in machine learning. And today we'll talk about an optimal control perspective on diffusion models to understand them better, maybe improve them, or kind of come up with new methods. Let's go.
Perfect. Thanks a lot for the introduction and the opportunity to talk here. I will talk about diffusion models and their connection to optimal control. And this is joint work with my two collaborators, Lorenz Richter at SUSE Institute and DIDA, and Karen Ulrich at Meta AI, where I also did an internship, and part of this work was done during the internship last summer. And generally we will be interested in generative modeling. So the task will be to sample from some complex distribution. It might be high dimensional, it might be multimodal with separated modes. Or sometimes also one is interested in computing some statistics of this distribution. And typically one is given samples. So typically the distribution is described by images, text, audio data, and one wants to generate samples which follow the same distribution as the given training samples. There's this other regime where one is given a density. This is typically the case in Bayesian statistics, computational physics, and chemistry. And today I will talk about both of those scenarios. And typically diffusion models are done for the first task. It's also the more common task, but we will talk about both in the following. Of course, there's a lot of generative models out there, especially based on deep learning. But as already announced, my talk will be on diffusion models, which historically originated from denoising, diffusion probabilistic modeling, and also score matching with Langevin dynamics. And they are, as I think everyone knows in the audience, state of the art for a variety of applications by now, but especially in this regime, which I introduced before, where samples are given. So the second regime of a density is not so often considered yet. And there's an example, for example, of the stable diffusion model, which is sampling condition in a text prompt of a photograph of an astronaut riding a horse. In this talk, we will particularly be interested in the SDE perspective on diffusion models. So diffusion models can be understood in the sense of a noising SDE, which basically component-wise transforms your data into approximately a Gaussian distribution, and then a denoising process or a reverse SDE, which again denoises the data or generates new samples. There's also different views on diffusion models based on variational autoencoders. For example, there's also connections to normalizing flows. But in this talk, particularly, we'll be interested in the connection to optimal control. So to give you a short overview of the talk, why are we interested in optimal control? This is a field which is decades old. So it arguably started with Bellman already in 1957, and then also work by Fleming and Richel and Ben-Soa later on, and many more. And the idea of this connection is to basically transfer methods from optimal control to diffusion models and vice versa. And to give you an example of why this can be helpful, in this talk, I will present two applications of this connection. First of all, we will derive the ELBO of diffusion models. Of course, this has already been derived, but we will show that via this optimal control perspective, this directly follows from a well-known theorem in optimal control. And the second perspective is what I already hinted at, using diffusion models to sample from unnormalized densities. And of course, we hope that there's many more such applications which can follow from this connection, and I'm happy to discuss and find new research topics in this direction. And we are also already working on extensions of this work. As I already said, in this talk, we will be looking at diffusion models from this SDE perspective. So we assume that the generative process is given by an SDE, and we will denote the density of this SDE. So we will first assume that it admits a density, which is given under suitable regularity assumptions. And then this density will denote by px, and it depends, of course, on the time, which we will consider from 0 to big T. To give you a short primer on this SDE-based generative modeling, so we will assume that the SDE takes the form which is written down here. So we have a drift, and basically this first part is just a common ODE, ordinary differential equation, and then the stochasticity is coming from this d-dimensional Brownian motion. So in this talk, we will focus on d-dimensional Euclidean space, but of course this can be generalized. And then the diffusion coefficients is governing the stochasticity part. And to give you a motivation or basically intuition of how such an SDE can be simulated, the easiest example is the Euler-Maruyama scheme, which is basically a simple time-stepping scheme. And we have here, this first part is just the Euler step for the ODE, and then we add this Brownian motion increment. And by definition, this Brownian motion increment is just a standard normal where the variance is given by the time delta. And yeah, here one sees a figure with like two Euler-Maruyama scheme trajectories for different discretizations. So the goal of SDE-based generative modeling and of my talk in particular will be how to learn this drift such that the terminal value of the SDE, so after time big T, approximates a given distribution, whereas this distribution might be given in the form of samples or also as a density. In the beginning, we focus on the samples part, and later on we'll come to the density. Of course, this can also be generalized, and one can also consider learning, for example, the initial condition or the diffusion coefficient. But for simplicity and also because of the connection to optimal control, we will be investigating learning the drift only in this talk. And that learning the drift only is sufficient shows a simple but also naive solution, which is given by this time-reversed SDE. So we can define an arbitrary inference or forward SDE y, which basically is defined by some drift f and some diffusion sigma, and which starts at our data distribution. And then by appropriately defining our generative SDE, we get back to the data distribution. So by appropriately, I mean we need to start the generative SDE at the terminal distribution of our inference SDE, and we need to consider this drift, which includes the score of the density of the process y, which is given by this gradient of the logarithm of p of y. And then it's even stronger because the reverse time SDE basically has the same marginals as the forward SDE at every time t. So basically they have always the same marginals, and there we see the drift of y, and we see the drift of x, basically transporting back the mass to the data distribution. And throughout this talk, I will use this notation with a reverse arrow to denote the time reversal. So basically it's just the time coordinate will be large T, so terminal time minus T. Why did I say this is a naive solution? Or why cannot we use it directly? The problem is that both the score as well as the initial condition depend on the data. So the score depends on the data because it depends on y, so on the density of y, and y starts by definition at our data distribution. And the terminal distribution of y, of course, also depends on y and also on the initial distribution, which again depends on the data distribution. So also sampling from yt is not straightforward. And we will see that diffusion models provide a working solution to both of those problems, and we will derive it via this connection to optimal control. And I want to say that this reverse time SDE, this theory, is quite old, and it dates back to Nelson, Anderson, Hausmann, and many others. So how do we get to this connection to optimal control and basically derive an objective of how to learn this drift easily from this connection? So the first idea is that we saw that the optimal solution is governed by this score, which again depends on the density of our SDE. So let's look at the density of our generative SDE, Px, and observe that it's well known that it satisfies a PDE, which is called the Fokker-Planck equation. So I have it here. So this Fokker-Planck equation is a parabolic second order PDE and it's linear. And basically it has this first part, which governs the diffusion. So D is just defined as sigma transposed, or sigma squared if sigma is just a scalar and not matrix valued. And then we have the second term, which is the advection or transport happening due to the drift mu. Then we also said we want to consider the reverse time SDE. So let us do a time reversal. So basically just reverse time, and then the PDE basically transforms quite easily just because of the chain rule. And if this minus sign, t minus small t, we get minus signs here, and this turns into a plus sign. And we can rewrite the divergences and also split the divergence of this product. So this last advection term splits into those two terms. And basically we see that this PDE is also a known PDE, which is called the Kolmogorov equation, maybe generalized Kolmogorov equation, because we have this zeroth order term here on the right-hand side. How does that help us? The idea is that this Kolmogorov equation is deeply connected to the HLB equation, so a Hamilton-Jacobi-Bellman equation, via a so-called Hopf-Cole transform. So there's a logarithmic transform or an exponential transform, depending on which direction one goes. And if one basically denotes by V the logarithm of this reverse time density, then one can do a straightforward calculation and see that V now satisfies this PDE, which seems initially more complicated because it involves this nonlinear term here, so this quadratic term. However, the advantage is that this HLB equation is very prominent in the field of stochastic optimal control. And this basically also establishes the connection we are looking for. So because this equation is so prominent, there's also basically a main theorem in optimal control, which connects this HLB equation to optimal control problems. And this will be the next topic after summarizing what we achieved for now. So for now, we basically just took a very general generative SDE. So no connection to diffusion models or so ever. We looked at the time reversed log density with a minus, and we found out that this satisfies this HLB equation. So, and now I come to the first application. Basically, there is a well-known theorem which connects this HLB equation to control problems. It's sometimes called verification theorem, but it's not very consistent across the literature. And now let us look at this theorem and let us find out how this directly yields the ELBO of our diffusion model. I want to also mention at this point, I already said that the ELBO has been, of course, developed before already. And one work which derives the same ELBO in this continuous time SDE setting is the work by Huang and others. And they basically stop at this Kolmogorov equation. And then they use Feynman-Katch formula, which can represent the solution to a Kolmogorov equation as an expected value. Then they use Girsonov's theorem, so they do a change of measure. And then they use the logarithm of this to get the log likelihood. And they use Jensen's inequality to interchange the order of taking the logarithm and integrating. And then they arrive at the same ELBO. And in this work, we basically argue that instead of doing these three computations, one can also just look at the HLB equation and use this verification theorem. So let's look at the verification theorem. This is the general theorem. I mean, it can be more generalized, but for this talk, I will consider this a little bit simplified setting. Then we see how this transforms into an ELBO. So basically, it tells you that given an HLB equation and a suitable space of controls, we can define all of those controlled SDEs, where we have some diffusion coefficient again. And here we have this control multiplied by the diffusion minus the drift. And if we then write down this stochastic optimal control problem, which is defined by running costs, So we have here this quadratic running costs plus this h, which comes from the HLB equation. This quadratic cost is a simplification, as I said before. So if one wants to consider a very general running costs, then one does in general not have a closed form solution of the HLB equation. And that's the reason why we focus on this quadratic term plus this h function. And then we have some terminal costs. Terminal, because here we basically evaluated at the terminal value of our SDE. And this is basically just the terminal value of the HLB equation. This is V at time large T. And then basically this verification theorem tells you that this minimum of this optimization problem is also given by the HLB equation at time 0, or by the expected value of it. And the proof is basically by doing Ito's lemma. So we just apply Ito's lemma to V. Oh, I see like a raised hand, yeah?
Yeah, can you maybe talk a little bit about why why the stochastic optimal control people care about this object? And now all of a sudden you talked about costs and running costs, terminal costs.
So basically you can come up with various of such optimization problems. I will actually mention one later on in my talk, but they can be physically informed or due to some other problems at hand. And then basically the direction is often that one defines such an optimization problem. One recognizes, oh, this is actually such a in such a scheme, because we have this SDE here, which needs to be controlled in a way to minimize such costs, which might be given, as I said, by some physics-informed problem or so. And then one has terminal costs, where one wants to penalize the control to end up at certain values in some sense. So it can be, of course, motivated from different directions, but given such an optimization problem, of course, the interesting question is, can we solve it? And this verification theorem just tells you, yes, in that case, if it takes this form, it can be solved by looking at the corresponding HLB equation and solve this PDE, which might not be easier, because also the HLB equation is a high-dimensional PDE and is in general not easy to solve. But it's just basically establishes this connection. Instead of looking at this optimal control problem, you can also try to look at this PDE.
Okay, so these optimal control people always have like some process that's happening, like some YS, but then they additionally have some control or some way to control this process, maybe towards something that's that they like. And this H can be a function of this process. And yeah, now if we maybe we have some cost over time, right, going from time 0 to time t, and when maybe if the process is in a state that we like, then the cost is low, and if it's not, then the cost is high. But then you additionally have some cost on this, and whether or not it's in a state that's nice or not, you can of course control with this u, but you then also have some costs on the control that you're doing yourself, like the direction and how much you're controlling it into some direction.
Yes, basically, we will see later on, this quadratic term can often be interpreted as some kind of entropy, which basically penalizes very large controls and motivates the control to stay close to a reference process, which is often just a Brownian motion.
Mm-hmm. Okay, and then this this verification theorem now tells us that if we have these quadratic costs and this nice thing, then the optimal controls, or the minimum u in all the allowed controls, so the u that we want to find, or the value of it is given by the expectation of the v that we also found in our HJB equation. Oh, and you already write, well, I think I'll let you talk about it.
No, I mean, that's a very good transition, because, of course, we have here this minimum, but we can also, so the verification theorem gives us also the minimizer. And again, the minimizer depends on the HJB equation. It is basically this diffusion coefficient times the gradient of the solution B. So it gives you both the minimizer and the minimum. And we look at a little bit different version of the verification theorem, just because it's more adapted to the problem which we are interested at. And this can be formulated as follows. So instead of looking at the minimization problem, we can also write down explicitly what's the difference. So basically, we know that the minimum of this would correspond to this. But if we don't take the minimum, there is a gap. And this gap can be explicitly written down. And this gap is basically just the difference, or the KL divergence between the process YU and the optimally controlled process YU star. And this KL divergence is on path space. What I mean by this is basically that this YU is an SDE, and it can be, or the solution to an SDE, and it can be interpreted as a random variable on the space of continuous functions. So basically, you always get the whole trajectory from 0 to large T, and there's a certain probability function on these trajectories based on how likely they are given the corresponding SDE. And then we can basically compute, as usual, the Kullback-Leibler divergence between two random variables, in this case on this path space. And this basically describes this gap between the minimum and the current control U. And now we just plug in what we found out before. So for now, this is just a general theorem for a general HLB equation. But we didn't have a general one, because for us, this H was the divergence of mu. So this is what we found out by doing this time reversal. So also here, this running costs adjust correspondingly. And then second, we also didn't look at a generic HLB equation, but we had V being defined as this time reversed log density. So if I now replace V all the time by this time reversed log density, and I also multiply by -1, and here I also undo basically this time reversal, then I will just get this following. So there's nothing happening except replacing and some very easy calculations. And we see immediately that the optimum corresponds to the scaled score. So exactly the quantity we are after in our time reversed SDE. And what we also realize is on the left-hand side, there's the log likelihood. So basically the logarithm of the density of our generative process given y of 0u. If this, for example, starts at the data distribution, then this would be the log likelihood. And we can interpret this KL divergence as the variational gap. And then we can interpret the expectation in the middle, just as the ELBO, which we can try to optimize in order to basically reach this scale score, and then in order to get this time reversed SDE. So when doing this, I just copied this ELBO and I removed the variational gap, and then we get this inequality. I again copied both SDEs. And this is basically also the ELBO which is derived in Huang. And in what follows now, I will just show you that this actually corresponds to what is used in practice, because many of you might not recognize this as the usual ELBO, which is used to train diffusion models. But also the material which follows now is mostly according to Huang, but it's nevertheless interesting for our second setting later on. So the first thing which we observe is actually we want to have the control on X and not on Y, because X should be our generative process and Y is the inference process. But we can do that by a simple reparameterization. So basically we just replace mu by sigma u minus f. So I basically marked it here in colors. So instead of this, we get just f. Here we have this sigma u minus f instead of mu. The same happens in the divergence term. And also the control now swaps from y. Here the control was at y, swaps to x. That helps us in the following setting, because we can now, first of all, interpret this as a prior loss. So this is just how well is yt basically approximating x0 of u. That's the log likelihood between those two. And we saw in the beginning in time reversed SDEs that we want those two to match. So if we start here at the data distribution and we use the result for our time reversal, then we know that the optimum, so maximizing this ELBO, actually leads to the optimal score. And if we would sample it correctly, so if we sample exactly the terminal distribution of y, x would end up at our data distribution again. But of course, we still have basically the two problems which we announced already in the beginning. This objective could potentially now be optimized, but it's still quite complicated. So can this be simplified? And we need this objective in order to learn our score. And we also didn't discuss how to actually sample x0 in order to generate data. And these two questions will be answered in the following. So first, how can we rewrite this loss in a more convenient way? And the idea is to rewrite the divergence and also to use a Monte Carlo approximation of the time integral. So if you look at our ELBO again, I just copied it here, then we do 3 steps. So we first see this is actually constant in U because x0 is just the initial distribution and this does not depend on the controller. So we can disregard this. The divergence of f is also constant. And basically, this divergence can be rewritten using the divergence theorem or Stokes theorem as the following product. And this is exactly the term which appears here if one expands the quadratic. So this is a quadratic. It will have as a first term u squared, which is basically this term, the 1/2 here. Then the second term will be 2 times this. The 2 cancels here, and the product is just given by this divergence term here. And the last term is just this squared, which is again constant in u and which falls into this constant. So in some sense, we showed that this ELBO, which I showed you before, which directly follows from verification theorem, is exactly the same as denoising score matching. So in this sense, we just learn that u represents this scaled conditional density. And I see again hands.
Yeah, just be careful with moving your mouse so fast.
Sorry.
We cannot really see where you're pointing.
Okay, thanks a lot. Yeah, so basically here, this conditional density, we will see later that this is tractable for some inference SDEs. And we can basically just use this mean squared error in order to learn the score. And what else did we do? We replaced this integral just by a Monte Carlo approximation, as I said. So we used, instead of the whole integral, we used a random time tau between 0 and large T. And then the second question, how can we sample? And how can we sample is by using specific kinds of processes. Why? Which approximately end up at a Gaussian distribution.
So the thing that you showed on the previous slide right now, this is the score matching loss that all the people use for training their nice diffusion models.
More or less. So in practice, one usually doesn't use the scaling and one does not learn the score usually, but the noise. But yeah, it's like a couple of steps away from this. And this is the one which actually corresponds to an ELBO. So the one in practice where one does not use the scaling does not correspond to an ELBO, but yields better results.
Yeah, I guess there are many reparameterizations of the score and ways in which people then train it.
Yeah, exactly. But it's just interesting to see that basically this ELBO can be rewritten in this very convenient way. And we will see later on that this is not the case for sampling from unnormalized densities, unfortunately. So coming to the second question, how can we sample? So basically we construct a process which ends approximately at a known distribution, mostly a standard Gaussian. And how can we do that? We look at so-called Ornstein-Uhlenbeck processes where the drift is given basically as this linear function. So it's just B of S times the process YS. and sigma is a diagonal matrix for every time s. And then we can just use the standard normal as an initial condition for x, which is approximately the same as yt. And one example of such a coefficient bs is given by the so-called variance-preserving SDE, where b is given as -1/2 times the diffusion coefficient squared. And then one can explicitly compute the conditional distribution of yt given y0, where this exponential here basically converges here to 0 and here also to 0, and the speed is governed by our choice of sigma here. And there's also results which tell you that, of course, one can pick larger sigmas here to arrive faster at our standard normal, but this also then incurs a higher discretization error. So there's a trade-off here. And basically you can summarize what we achieved. So we have these two SDEs, the variance-preserving inference SDE, which approximately ends at a Gaussian, where this approximately is governed by our choice of diffusion coefficient. We have the generative SDE, which starts at a normal distribution. And we have our ELBO, or our optimization objective, which basically lower bounds the log likelihood by the score matching objective, where we can explicitly compute the conditional density, as we saw before for our special case of Ornstein-Uhlenbeck process, which we defined. And so basically we saw via this verification theorem and then a couple of rewritings of this ELBO, we arrived at one, as we said already before, one of the variants which is typically used in practice to train diffusion models. And while this has already been quite interesting and offers a new perspective on this ELBO, for example, we also saw this variational gap in terms of path measures. This has, of course, been, the ELBO has, of course, been known, but now we come to maybe even more interesting parts. So how can we use this framework to develop diffusion models to sample from unnormalized densities? And to set the definitions again, so we assume now that the data distribution admits some density, where the normalizing constant may or may not be known. And basically just this function rho is known in general. And the problem here is that we cannot use the previous ELBO, which we just derived. Why cannot we use it? Because we would need to simulate y. And this y depends, of course, on the initial value y0, and y0 depends on the data distribution. So we need samples from y, from data distribution in order to simulate y, and in order to then use this denoising score matching objective. So how can we move forward? The idea is, okay, in this objective, we had an expectation over y, but we actually would like to have an expectation over x. So the idea is to interchange the role of x and y, and again, use the verification theorem. So basically, before we had the H-B equation for this minus logarithm of p of x. Now we will do the same just for minus logarithm of p of y, because we did it for a very generic SDE that works exactly the same, basically. Just that we get a different drift here. And the difference is now that basically if you apply the verification theorem as before, we get x as a controlled SDE directly, so we don't need any reparameterization. And also our expectation is over x now. And we can simulate x because x starts just as a Gaussian, for instance. And then we can simulate x and basically try to use this objective. So this might not look like an objective which seems sensible, but we can rewrite that and see in a minute that this actually corresponds to a typical reverse KL objective. So I just copied the statement from the verification theorem here, which is the same as we saw before for diffusion models with data given, just that we interchange the role of x and y. And then I bring this reverse KL divergence on the left-hand side. I bring the rest to the right-hand side, and I use the fact that we start our inference process at the data distribution. So we know that the density is just given by rho over the normalizing constant. And this basically gives us this term rho here, the normalizing constant here, because we have the logarithm, this can be split. And we have here this term which comes from this term from the left-hand side. Exactly. And so this is a sensible objective. So basically it tells you, maybe it can even make it more explicit by saying that this is a constant, so we don't need to consider it during the optimization. And y large t is just the terminal value of our inference process. So this is just given by a Gaussian. For instance, a standard Gaussian if we have this variance preserving SDE, which we defined before. And if you want to have it even more explicit, we can use the disintegration theorem and rewrite this reverse KL divergence as a KL divergence between XU and Y reverse. So this is the reverse time SDE, which we saw in the beginning. And then we get some Breyer loss penalizing the fit here at this terminal time t of the inference process. So basically this does not depend on U. And this just tells you that this objective tries to match XU to the time reversal of Y. And as already said, we can actually optimize this objective. We can simulate it and optimize it, and let us go into more detail of how this can be done. So we call that the time reverse diffusion sampler, or short DIS. And I just copied the objective from before, where I already assumed here that the drift f is chosen in a way that p of yt is approximately a Gaussian, so I replaced this by a Gaussian. And I already said that we can unfortunately not use this denoising score matching, because now here the expectation is with respect to XU, which helps us that we can even compute it, but unfortunately it prevents us from using this Monte Carlo approximation, and we need to also simulate XUT until the terminal time t. So the approach is to discretize this objective, so discretize the integrals, discretize the SDE using the Euler-Maruyama scheme, parameterize U as a null network, for instance, simulate the whole trajectory already using this network, because the trajectory depends on this function U, and then backpropagate through this SDE solver. One can, of course, in the memory constraint setting, also use the stochastic adjoint method in order to basically minimize this objective. As a small trick which we used, which improved performance, is to use the knowledge we have on the optimal control. So we know that the optimal control is just the scaled score, and we know the scaled score at 2 points, namely at the initial time, because there is just a Gaussian, and we can compute the score of this Gaussian, or it's approximately a Gaussian. And we can also compute the score at the terminal time, or the initial time of Y, depending on how you view it, because this is just the data distribution. And we know that the data distribution is rho over the normalizing constant, and taking the logarithm, this will be an additive constant, which disappears due to this gradient, which we take here. So basically, we can, for instance, use a linear or some other interpolation between those two values as a reparameterization or initialization scheme of our neural network. And yeah, we tried that out, for instance, for this double well problem in 20 dimensions with 2 to the 5 modes. So we have basically those, in this case, 5 double wells given by this term here. And then we have 15 Gaussians given by this term. And one sees here a little illustration for the first 2 coordinates. So at the beginning, just for the first coordinate, and then here a KDE plot for the first 2 coordinates. And we see that it well recovers the modes of our distribution, although they are quite separated, and the problem is quite high dimensional for such a sampling problem. Of course, we want to compare this method also to other methods. So what we did is we compared it to the so-called path integral sampler, which originated from actually a substantial amount of work in stochastic optimal control, which did similar stuff, also concurrent, and which is based on a Schrödinger half-bridge problem. So basically, for this stochastic optimal control problem, one wants to find a controlled process which minimizes the KL to an uncontrolled process. So just if the control is 0, this is this 0 here in the superscript, such that the terminal value of x is distributed like a data distribution. And it's a half-bridge problem because we only specify here this terminal condition, and we assume, so this is the reason why it can be solved in this scenario, that the basically the reference process and also the control processes, they start at a delta distribution. So they all start at a single, can be arbitrary, but usually it's 0.x0. And then one can write down what is the objective. So it's again such stochastic optimal control problem where we have running costs just given by the quadratic. And we have this terminal costs given by the quotient of the density of x uncontrolled at time t, evaluated at x controlled time t, and here rho of x at time t. And in many cases, so in order to basically compute this density, so what's the density of the uncontrolled process at time t, one can, for instance, use just a scaled Brownian motion. So one sets the drift to 0 and the diffusion to 1, for instance, 1 over square root of t, such that the uncontrolled density is just a Gaussian with variance 1. So this piece objective is another example of such a stochastic optimal control problem. And basically want to compare those two and also see what's the difference. So let us quickly write them below each other. So what's exactly the difference now? First of all, we see that we have this additional running cost, which is given by the divergence f. This additional running costs originated from the fact that we did this time reversal. And then we have a generative process which is initialized, or which has an initial distribution, a Gaussian, whereas the path integral sampler has this delta distribution. Furthermore, they have here the density, so this normal random variable, k, or density of this standard normal, originated from the fact that this is the density of the uncontrolled process at time xt. Whereas our density here originated from the fact that y capital T is approximately distributed like a Gaussian. So basically, in our case, in the this sampler, the choice of drift governs here the density of yt, whereas in the path integral sampler, the choice of drift governs the density of the uncontrolled process xt, 0. And so we can use different SDEs and initial distributions. We can, of course, also use a scaled normal distribution. And maybe more importantly, this allows us to transfer techniques for diffusion models. For example, successful noise schedules, probability flow ODEs, or also exponential integrators to the sampling problem. And the hope is that we can also improve upon the sampling problem, upon this task 2, by using techniques developed for this task 1. At this point, I also want to mention that there's concurrent work, which also looked at how to develop diffusion models for this task. And they basically developed a little bit different route of how to establish such a reverse KL divergence. And they arrived at also a different objective, which basically looks like the piece objective, but they can also use an Ornstein-Uhlenberg process like in diffusion models, and they can also sample from a Gaussian. So basically this is somehow in between the two approaches. So why they can use here initial conditions, which are not a delta distribution, they still use the same objective, and they don't have this divergence term and this term here. Whereas this term is actually not dependent on the control at all, because x0 of u does not depend on the control, so we don't need to use that during optimization. Whereas this term depends on the control because it's x at large time t.
So is there nothing different in the denoising diffusion sampler paper beyond what you just said?
I mean, the difference is that they can basically, they don't rely on this delta distribution. So they can also transfer techniques for diffusion models. And they can also use those more general SDE processes. But the objective itself looks the same. And basically, they have a different way of representing this reverse KL divergence. So if we remember, basically, where is it? Here we had our reverse KL divergence. And just that expression here is not tractable because it depends on the optimal control, which we don't know. So we need some way of representing this reverse KL divergence. And we basically took the route of going by this verification theorem, which is very similar to how the ELBO is derived. And they basically work more with a reference process and then showed that a suitable reparameterization also leads to a tractable objective for this reverse KL, which then in the end turns out to be the same as the piece. Where do we have it? Yeah, as the piece objective.
Okay.
So let's look at some numerics of how this works in practice. So at the first task, we analyze to compute expectations. So basically we want to compute expectations of our data distribution. So y0 is just distributed like our data distribution. And this might be interesting for various scenarios of f. We analyze just here this quadratic and also the L1 norm. And then basically we trained both this path integral sampler and our sampler, and then computed those expectations for different numbers of Euler-Maruyama schemes in the evaluation. So for training, we basically start with a very coarse discretization and then make it finer and finer during training. But for evaluation, we can basically try to evaluate with different numbers of steps. Those steps are typically higher than for diffusion models used for sampling from a distribution where one sample is given. And we also saw that like for less than 50 steps, for example, the results are quite bad. So there's also still some work to be done. But also on the other hand, those problems are not as high dimensional. So we're not dealing with like natural looking images, high quality images, but already 50 dimensional problems are very hard to sample from as soon as the modes get quite separated. And there's many different modes. And we can now compare basically the expectations given by this path integral sampler and our sampler and to the ground truth, which we can compute for this double well example because it just separates in the dimensions. And we see that our sampler is generally better at approximating those expectations. And this is some kind of metric to judge the global sample quality because it takes into account basically the samples on a global level. And for task 2, we looked at the different task of computing log normalizing constant. So if you remember in our objective for the reverse KL, we said that the log normalizing constant is actually just a constant, but basically we can by using this, or by computing this constant, we can also try to approximate the log normalizing constant of a given distribution. And we can also use important sampling in path space. So basically, we also get we can eliminate the bias at the cost of a higher variance in order to compute those log normalizing constants. And this example shows here 3 distributions, a 2-dimensional Gaussian mixture model with 9 modes on a regular 3x3 grid. Then a well-known example for MCMC methods, the funnel distribution, which is given by this Gaussian in the first component, and then the exponential of the first component as the variance of the Gaussians in the other components. And then we also tried out for the double well example, which we looked at before. And we again look at the results for various numbers of integrator steps, and again see that the estimate we get using our method is better than the previous method, where I also want to emphasize that we improved also upon the path integral sampler. So we used basically a little bit more compute in terms of larger batch sizes and longer optimization routines, because we observed that then convergence is better. But using exactly the same settings with our sampler, except of course things which are different in both methods. So, but we try to make it as comparable as possible. We could outperform this path integral sampler and also have been more robust during training. Yeah, this summarizes my talk. So just to give you a quick overview again, what we saw, the takeaways are diffusion models via some PDEs can be connected to the HLB equation. This is quite general for all generative models, which are SDE-based actually. Then we can use tools from optimal control, which is a quite old and well-established field, to easily derive the ELBO, and also get new intuitions on how basically the variational gap looks like, and also how the problem is behaved in the path measure space. We can also use exactly the same derivation, just with a basically interchanged role of X and Y to derive an objective for sampling from unnormalized densities. And as I said, we are still working on further methods in this direction. So basically improving upon this sampling for unnormalized densities, which is currently under investigation using better loss functions, and also coming up with like more elaborate ways inspired by recent techniques and diffusion models. And of course, I'm happy to discuss further follow-ups or further connections and applications, so let me know. And yeah, thanks for your attention, and I hope you like the talk.
I did. Okay. Then let's get to some questions. Oh no, first thanks for the talk, and then let's get to some questions. We have in the chat right here. We'll start with questions from other people first, I guess, before we get to my stuff. Can we use other costs for optimal control and design the advection term accordingly?
Can we use other costs for the optimal control? And at which point exactly?
Yeah, I'm also not sure how this would be answered.
So basically,
or maybe there's a confusion with the with how the cost that you or the cost for which we're finding the optimal U, how this cost arises.
Yeah, so that's what I also want to explain. Maybe this is so I actually did not have any choice in setting those costs. So basically this cost directly originated from the HLB equation, and the time reversal produced this divergence term. And for the path integral sampler, this cost basically arises from the fact that I want to be close in the entropy sense or a KL sense to the reference process. And this terminal costs in both scenarios arise from the fact that I actually want to end up at my distribution, which is given by rho. And similarly, in the ELBO, which I derived in the beginning, also this originated from the HLB equation. And yeah, so we basically use this more as a tool. We didn't go the other route of designing our own objective, our own running costs and terminal costs in order to achieve a certain optimization problem, but we used this in a way to get an objective in order to solve this HLB equation. Because we know that the HLB equation governs the densities, and we are interested in this score in order to optimally control our SDE.
Okay. Yeah, so we can confirm to the chat. So you do not have any freedom in choosing it in that sense. Yes. Mm-hmm. Okay, but you now have this nice you now have a way to train your diffusion model to sample from an unnormalized density without any data from the distribution, or without having any data points from the distribution to train it. Cool, but we could also train some other generative model. Some other generative models, and people have done that a lot with normalizing flows, right? And with normalizing flows, you can then do some nice tricks like training with the forward KL instead of the reverse KL, and aiming to optimize other training objectives where you then generate your data and use it later on, or you generated data and then use it later on in some other objectives that are more that encourage to cover the modes and to be more mode covering than the reverse KL. So why would I ever use a diffusion model for sampling from unnormalized densities if I cannot then do all of these nice things like using forward KL?
Yeah, so of course, very good question. And this is of course the somehow for practitioners, the takeaway, like when or why should I use this? And it's important to say that the path integral sampler paper compared itself to, I would say, basic MCMC methods and also basic normalizing flows and outperformed them. But one also needs to say that taking more elaborate versions, more elaborate MCMC methods, or also more elaborate stochastic normalizing flows, for example, one gets often better results than these diffusion samplers. But as I also said, we are just in the beginning of improving it and basically using techniques developed for diffusion models for this setting. There is, for example, some ideas which we are currently investigating is that the HLB equation can also be tackled using null solvers for PDEs. So for example, we can use pins, physically informed neural networks, or also there's other methods how to solve HLB equations using neural networks. And this can act as a pre-training or as an additional loss for our training in order to counteract this basically mode collapse, which the reverse KL might incur. There's also another way of basically picking. So now that we have this path space measure interpretation of our problem, we can also look at different ways of penalizing the discrepancy between, so we basically have here the discrepancy between, let me take a step back, between the optimal or the time reversed SDE and our generative process. And we also experiment with different ways of basically penalizing this mismatch and getting more stable objectives, which lead to better results. So we already validated that, for example, on the alanine dipeptide problem, where we cannot yet achieve the results, for example, which are done by combining normalizing flows and annealing methods, for example, which lately showed, I think there was also a presentation in the seminar, we showed how to get this without any samples. But using this other loss, for example, in the pre-training scheme, we are already getting closer to that. And of course, that would be also interesting to combine this path integral sampler methods with MCMC methods.
Yeah, the normalizing flow paper that you're referring to, or the flow annealed importance sampling bootstrap paper that you're referring to here, which is nicely able to sample from the unnormalized density of alanine dipeptide, which arguably is a extremely much more complicated distribution than these double wells and 50 dimensional whatever 50 modal distribution that we looked at as well. Yeah, they're able to sample from this pretty nicely. And also Vincent is in the call right now. Yeah, if we, yeah, maybe we can talk about that a little bit. If you try to, like, are there ways to use your diffusion sampler to train with other training objectives, like that are mode covering? Because in their paper, they make a pretty big deal out of the fact to train with mode covering objectives instead of with reverse scale.
Mm-hmm. Yeah, I mean, basically one could try to go a similar direction as they did, because of course also the diffusion model leads to a normalizing flow by this probability flow ODE, which one can then treat as a normalizing flow. And as I said before, we have additionally the idea of using the PDE solvers to counteract the mode collapse. And we've also thought about similar losses then in this paper, using the variance in some sense instead of the plain reverse KL divergence, which basically minimizes or like basically optimizes this effective sample size instead of optimizing this KL divergence. And this already improved significantly our results. As I said, this is still ongoing work, and I hope that in some sense it will be possible to basically see for which scenarios normalizing flows might be better, for which scenarios those diffusion-based samplers might be better, where we have like now 3 different kinds of options, or maybe we can even combine them and also make the best out of the 3 options we have: MCMC methods, normalizing flows, and diffusion models. Yeah, this is of course future work still.
Okay,
so I would yeah, but I just want to conclude basically, like for normalizing flows, there's like, I think, much more history and like work done already, which you can build upon. And for diffusion models, we are, I would say, just the beginning of developing such samplers. They have been developed in the field of optimal control, as I said already before, but also the first deep learning based approaches only appeared in the last few years in this direction.
Then I'm looking forward to that future work coming up. And also I'm very happy to see that Vincent is raising his hand and maybe can tell us something about the paper or something else.
Yeah, I mean, actually, I'm also looking very much forward to follow-up work on this. So one advantage I see maybe between this connection of optimal control and diffusion models is maybe there have been some works in the optimal control literature completely disconnected from diffusion models. Some maybe advanced techniques, some results which could be translated through this connection now to diffusion models. Do you think there's anything like that, basically that optimal control or works in optimal control could inspire like some novel diffusion kind of methods through this connection?
I mean, this is of course like one of the main topics we're investigating. That's also why I put those question marks always as like a follow-up of this work, because we're of course currently going through the literature and talking to other researchers working in this field. If there is a potential to transfer methods, there are methods maybe from nonlinear filtering which could be used. But one of the things, optimal control has not been looking too much into very high dimensional problems previously. So this is maybe one of the limitations, and it's not so directly clear to us what could be used in that field. So for now, as I also presented in my work, we transfer more from diffusion models to the optimal control and not vice versa, but of course hope that this might also be possible. But if you have any ideas, I'm happy to chat.
Yeah, but I'm not an optimal control expert. I mean, I actually did a little bit of work on optimal control in my bachelor thesis, but yeah, it was also on like relatively small systems, and my experience was similar than yours, that usually you restrict yourself to relatively small systems there, while typically the diffusion models, you want to apply this to large systems. So I understand. I mean, I'm not surprised to hear that you haven't found anything in this direction yet. While maybe there's still stuff out there, and we just haven't digged deep enough yet.
Yeah, exactly. So that's what I'm hoping for. There might be, of course, also ways to forcefully add other running costs in order to basically include physical knowledge into the problem. But this is more like a different direction then, which has already been done for Schrödinger bridges, for example, which is of course is also interesting to go and try to find like basically more connections to Schrödinger bridges and vice versa as well.
I see. Yeah, really interesting.
Yeah, and I think like including additional costs there, including additional costs, maybe then we can encourage the model to, so to say, stay on the manifold of low energy conformers. For example, if we're talking about now sampling the Boltzmann distribution of a molecule like alanine dipeptide, and to not like produce bond lengths and bond angles that are very unrealistic, and we can sort of bias our diffusion model with additional terms to respect the energy function that is that we're trying to sample from. Okay, but
yeah, I just wanted to say that basically here, for example, this quadratic cost is, as I said, just coming from this prior of basically just having Brown in motion. And here this comes from the fact that we exactly want to match the reverse time SDE, but of course it might be beneficial to think more about problem-informed ways of defining that.
Yeah. Okay.
Yeah, that was a very interesting talk, and like it reminded me of like when I was working during my end of my bachelor and my master's. I was working on like robotics control, and how we can when we want to go, like, let's say, from one position to another position, and we'd like to control that and avoid like having oscillations and noise around that position. Of course, here it's a lot more complicated because it's like from one distribution to the other, but it's still I find it very nice to see that you can bring a connection between the optimal control and the diffusion model. And like, if we can, one of the issues right now with diffusion model is that when trying to denoise, there's a lot of oscillation and like more noise going on, and you need many steps to converge. And maybe with like optimal control, or just generally borrowing ideas from how like planes are controlled, because when you move a plane, you don't want it to oscillate a lot around the objective. You want it to reach the objective smoothly, and how this can affect like the speed of convergence and things like that. So it'd be great to see like how borrowing these kind of things from the from control theory can really help make the convergence faster, less noisy, and easier to converge. So I think it's like right now this presentation was like very mathematical and really into the equations, and hope that like next year we get like the follow-up presentation about like, hey, like diffusion models are now 3 times faster to converge because we use that kind of control. So very exciting work.
Yeah, thanks a lot. Thanks a lot. Of course, it's like optimal control or HLB equations also immediately lead to topics like reinforcement learning. We also hope that we can transfer this back to diffusion models, improve them further. And yeah, as I said, we are already currently working on extensions, and I hope to return in a year and present some applications and new stuff in this direction.
Excellent. Many thanks to Julius for these nice insights into his optimal control perspective on diffusion models or score-based generative modeling. And he's saying there's a lot of exciting work coming up. I definitely hope so. And maybe you can contribute to that exciting work and leverage the stochastic optimal control perspective to improve our methods in diffusion models and something for our normalized densities. But if you just want to enjoy future reading group sessions yourself, all the information is down in the description, and maybe see you next week or any other week.